We're talking related rates today, which is essentially related rates. All it is essentially is a application of implicit differentiation. Okay, so it's just implicit. The only difference is now we're going to be using real world examples. Okay, so far, okay, in differential calculus, related rate problems involve finding a rate at which a quantity changes by relating that quantity to other quantities, which is called, that's why it's called related rates, because these things are related somehow, whose rates of change are known. The rate of change is usually with respect to time, because in the real world, the only thing that's always happening is what? Time, right? It's always going. So every time we take a derivative, guys, it's always with respect to time with these related rates problems. It's always going to be with respect to time unless we tell you otherwise. Okay? So, I'm so glad that my board is working because I did not want to write all this on the whiteboard because I want you to write it, not me. So, do me a favor, copy this example down, okay? And then we are going to break it down and figure out how to solve it using related rates calculus, okay? All right, so related rates problem, guys, it requires you to have a lot of prior knowledge. And I don't just mean of math, I mean sometimes of physics, and honestly just real world. My hope is that everybody at this point in their life has blown up a balloon, okay? Because if you haven't, then this might seem really weird to you. But if we've all blown up a balloon, we know what's going to happen when we push air into it, right? So here it says, here's this first example. It says air is being pumped into a spherical balloon at a rate of 5 cubic centimeters per minute. So, already, what's happening to this balloon? It's getting bigger, right? Okay, air is going into it. Good. Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. Okay? So, what do we got going on here? First of all, I want us to understand, first we have to identify what information that we've been given and what we want to find. So guys, what kind of situation is going on here? What's increasing? The air in the balloon, which is called volume. Does everybody see that? We're talking about volume here. Okay? Volume of what? How do you know it's a sphere? It says a spherical balloon. That's important, right? Because, yes, we know back in geometry we did volume. I know how to do volume, but of what shape? Well, it tells us a spherical balloon. Does everybody understand that? So we're talking about volume. And there's also another clue here. There's also another clue that we are talking about volume. Anybody else see it? The cubic centimeters, right? Remember, volume is always in cubic units, right? So we are talking about volume of a sphere. Okay, so we're talking about volume of a sphere. Does everybody agree with that? So we have to have. I know I'm gonna take a derivative at some point. So don't I need an equation? Does anybody know the formula for volume of a sphere? Okay, so we're gonna have to start remembering these things. Okay, so of course this is the first time you've seen it in a while. So volume of a sphere is 4/3 pi r cubed. Okay? Volume of a sphere is 4/3 pi r cubed. Okay? Does everybody understand what's represented in the, what do I need for this? I know I need a radius, and then it's going to tell me the volume. Okay? So guys, what was I given? What was I given? The what? Diameter of 20 centimeters. So if the diameter was equal to 20 centimeters, what else do I know? Okay, so the radius is equal to 10 centimeters. Does everybody else understand what we're given? Okay. What else was I given? So, rate of change, guys. Rate of change means what? Slope, which in calculus means? derivative, right? So when we're talking all of these guys, because obviously we're obviously in calculus, so we're going to be taking a derivative. So I have, does everybody see that I was given the rate of change for what? The volume. So I was given the rate of change for volume. Does anybody know what I call that? How do you suppose you express a rate of change, basically a derivative of volume? dV dt. Does that make sense? Because it's the rate, it's the volume changing with respect to what? Time, right? Because it's taking time to fill this balloon up. Okay? So I was given the rate of change for volume called dV dt, which was what? 5. Right? My rate of change for volume is 5. Okay, 5 cubic centimeters per minute. Okay? What do I want? So this is all the stuff I was given, correct? This is all the stuff I was given. What do I want? It says determine the rate at which the radius of the balloon is increasing. So they want to know the rate at which the radius is changing. Does everybody see that? So that we want the rate of change for radius Jeez Louise, that's loud. We want the rate of change for radius called what, people? What do you think I call a rate of change for the radius? Very good. Okay? Is everybody with me? So I want dr dt. Okay? Because that's the rate of change for radius with respect to time. We good? Okay, so that's always your first step. Your first step is understand the situation. Okay? Probably figure out what kind of formula we're going, because we're going to need an equation, right? We always need an equation. So you figure out which equation you need, figure out the information that you know, figure out the information that you want. Okay? The next step is now we're going to take the derivative of both sides of the equation with respect to time. So my equation, once more, was v equals 4/3 pi r cubed. Correct? Now I want you to take the derivative of that equation with respect to time. Okay? So, on the left side I just have a v. What's the derivative of v? Well, 1, right? And then basically, because I took a derivative, dv dt. Agreed? Equals to, now on the right side, this is where a lot of students, for some reason, still make a mistake. How many variables do I have there? Just one. R. Pi is not a variable. Right? Pi is a constant. So basically, guys, this is just a simple power rule. Because it's like fourth number, right? R cubed. So just take the derivative. What do you think is going to happen? The 3 is going to come up front, right? Because it's a power rule. So what's 4/3 times 3? The 3's cancel, right? Because you're multiplying by 3 and then you're dividing by 3, so the 3's are going to cancel. Or basically think of it as 12/3, which is just what? So it's just going to be 4 pi r squared, good, dr dt, because I took a derivative with respect to r. Are we good with that? Any questions? Okay, I'm going very slow. Okay, I'm going very slow. So, I took the derivative. We good? Now the last step is plug in what you know and solve. Look what I have. Look what I have. I have 3 different things here that's available for me to plug in. What are the 3 different things? dV dt, a radius, and dr dt. One of them I don't know. Which one? Why? How do I know I don't know that? That's what I'm trying to find. So obviously, do I know the other 2? Hopefully I should. I know my radius, which we already said was what? And I know my change in volume, which we already said was what? So plug in what I know and solve. It's just now it's an algebra problem. So this is going to look like what? 5 equals 4 pi 10 squared times dr dt. Okay, guys, well, if you're trying to solve, okay, so simplify, of course, what would I get here? 5 equals to, I would say, 400 pi. And here's a little trick, guys. Don't multiply that pi out. Just leave it. Okay, so 400 pi is a perfectly acceptable answer. Times dr dt. Whoops. And if I'm trying to solve for dr dt, I'm trying to get that alone, what am I going to do? Divide. So dr dt is equal to what? 5 over 400 pi. Can I reduce that? So this is going to become 1 over 80 pi. 1 over 80 pi. So this is my dr dt. So you have to understand, what does this represent? So yeah, that's the units, right? So this represents the rate of change of the what? And I do want you to understand something. Is this a positive or a negative number? And why is that? Because it's increasing. Right? It's increasing. So this doesn't this is where a lot of students kind of make their mistake. This doesn't represent the radius, right? This is not how long my radius is. This is what? How much it's changing. And then, so the units actually come in handy here. This is 1 over 80 pi what? Centimeters per minute, right? And it's not cubed. How do I know it's not cubed or squared, actually? It's just a length, right? It's just a length. Okay, so lengths are normal, right, to the first power. Areas are squared. Volumes are cubed, okay? So this is actually 180, or I'm sorry, 1 over 80 pi centimeters per minute. So every minute, my radius is increasing at 1 over 80 pi centimeters. Okay, so it's just getting that much bigger every minute. Does everybody understand what we're going to do? Okay, processes, it can get confusing, trust me. Okay, it does get confusing. Any questions so far? You sure? How is this real world? Good question. Balloons do exist in the real world. So this is a very simple equation, obviously, right? So it can get as complex as, think where you're going to do a problem today where something is moving in an elliptical pattern, and I've talked about that before, right? So think about what in the real world moves in an elliptical pattern. A planet. We do, right? So wouldn't it be interesting to know how fast it's changing, especially if I say want to intersect that planet? I don't know, isn't there a mission to Mars coming up pretty soon, right? So wouldn't it be, it's not like we just fire a rocket and hope we get there, right? No, there's calculations going on. So this is the stuff they do. This is the stuff they do, right? So this is what NASA's doing on a very elevated point, right? This is very basic, okay? So let's try again. Let's try again. Again, I'll give you time to copy this down. All right, here we go. Okay, example number 2 says, a 15-foot ladder is resting against the wall. Automatically, what are we talking about here? A what? A triangle. Very good. We're talking about a triangle. More specifically, hopefully, unless it's a leaning wall, right? But if it's a good wall, okay, if it's a good wall, and then I have my ladder, right? I'm not an artist, so. Okay, I have my ladder. So, and then obviously I already know what about my ladder. It's 15 feet. Okay. The bottom is initially 10 feet away from the wall and is being pushed towards the wall at a rate of 1/4 foot per second. How fast is the top of the ladder moving up the wall 12 seconds after we start pushing? Okay, so that's a lot of information here. Okay, what else do we know? I know that it's how much? So from here to here is 10 feet, right? Okay? And what is happening to this ladder? Okay, so two things are happening. I said like this. Two things are happening. What am I doing to the bottom of the ladder? Pushing it towards the wall. So does everybody see that it's going this direction? Okay? So say that again. Steeper? Is that what? What's steeper though? Like the ladder itself, like the slope of the ladder. I get that. But you said something interesting. It's what? The bottom is decreasing. Y'all hear that? It's decreasing. Okay. Um, and I actually know how fast it's changing. Right? How much? 1/4. But he said it is decreasing. So it's actually negative 1/4. And what do y'all want to call this? Now here's the thing, because like in this case they didn't tell us everything, right? I can call it technically everything, but don't make it hard on yourself, guys. What is usually, this is usually my what? X, and this is usually my what? So can I call this X and call this Y? So if that's the case, then what do I call that change? Dx dt. Agreed? And how much? I know that that is how much? Why is it negative? You really have to understand that, okay? It's negative 1/4 foot per second, okay? So guys, like I said, this is real world. So hopefully, I'm not sure if you've ever pushed a ladder towards a wall, but what happens to this ladder, you're smart enough to figure out, if I'm pushing the bottom this way, what's happening to this thing? It's rising, right? It's rising. So this thing is going up, okay? And so then what do I call this change? Okay? dy dt. Now it says here, they want to know how fast is the top of the ladder moving up the wall. How fast is the top of the ladder moving up the wall? So they want what? So does everybody agree we want dy dt? Right? We want dy dt. And then something interesting says, how fast is it moving up the wall? 12 seconds after we started pushing. So I have a time limit, right? This is not infinite. I'm only going to push for 12 seconds. Okay? So, I also know something. They're giving me that for a reason, okay? I know that I'm pushing at negative 1/4 feet per second, right? I know that I'm pushing, well, that's the change, I'm sorry. I'm pushing at a rate of 1/4 foot per second, and I'm pushing for 12 seconds. So really, you guys have figured out, right? You can figure out where I'm going to stop. Does that make sense? So what does that represent? The x. I can figure out what x is, okay? Because it started off at what? 10, and I know it's going down 1/4 foot per second. Agreed? And so then you guys, 1/4 of 12 is what? 3, so 10 minus 3 is. So this represents what? What does this represent? This is basically after 10 seconds, that's my x, right? So this is after 12 seconds. Okay? So I did what I wanted to do in my first step. My first step is figure out what you have, figure out what was given, and this wasn't essentially given, but it was, right? It's something I can easily figure out. Okay? We good? Okay. The next step is to figure out what kind of equation I'm going to use. Well, guys, what shape do we have? A right triangle. Is there a familiar right triangle when it deals with the side lengths of a right triangle? Good. So let's use the Pythagorean theorem. Okay? Let's use Pythagorean theorem. What do I know? Okay, except I use what? So I use x squared plus y squared equals, and then I actually already know c. C was what? 15 squared. Is everybody good with that? Okay, so I can even simplify this even more. So I know x squared plus y squared is equal to what? We good? So Tracy has a good point. She goes, well, don't we already know x too? Like, and x is, well, 10 at the beginning and then it's 7 at the end. You are correct, but remember, we have to do this. In order for us to find the rates of change, I still have to do what first? Derivative. So I'm not going to plug in until after I've taken the derivative. We good? So that's my next step. Let's take the derivative. Let's take the derivative. So what do I got? 2x dx dt plus 2y dy dt equals 0. We good? Okay. So now that I have, again, what do I want? Dy dt. So basically I should know everything else, correct? So 2 times, and what's my x? Okay, so now this is where, is it the 10 or the 7? I want to know after 12 seconds, right? I want to know, because I want to know if something has changed. Okay, so it is going to be my 7. What's my dx dt? Negative 1/4 plus 2. Okay, so good. So y, I don't know it. They didn't give it to me. But like Vanessa said, we could figure it out because I know that it's a right triangle. I know my ladder is always going to be 15. I know my x is what? 7. So then can I figure out y? Yeah. Okay, so we're going to have to do a little side work here. So then, what do I got? Okay, so 15 squared minus 7 squared equals y squared. You should probably have calculators, right? Unless you're all geniuses. I would get a calculator, guys. Get up, hurry up. You're going to need it. Okay, so I have 15 squared minus 7 squared, which is 225 minus 49, which is what? So you should get 176 equals y squared. Therefore, y is equal to what? The square root of 176. Do you think I want a decimal? No. I can. You can give me a decimal, but not to the end. Okay? Not to the end. So I know that y is 170 square root of 176. And then I don't know dy dt. And I know that's still equal to 0. Okay, guys, so this is now an algebra problem. This is now an algebra problem. Solve for dy dt. So you want to simplify this or what? Okay, let's make this easy on ourselves. Right now, this is all negative, right? This is all negative because they're all being multiplied by a negative. So then when I move it to the other side, it'll be what? So I can write it as 2 times 7 times a positive 1/4 now. Over. Now, no, look what I'm keeping the numbers for a reason. And then I'm going to divide by what? 2 times square root of 176. See why I kept the numbers? What's going to happen? 2's are going to cancel. Okay, so basically I'm reducing all at the same time. So 7 times 1/4, of course, is 7/4. And then over the square root of 176. And then at this point, guys, I would take, don't sit here trying to rationalize the denominator and all that. I would take a decimal at this point. Okay, so in your calculator, can we put that in? Make sure you put it right. Okay, I would actually use the fraction function. Use the fraction function on your calculator. So you're going to put a fraction within a fraction. One three. Yeah, that's what I was like. So I got 0.1319. And so what does this represent? And based on the number, does that make sense? Is it a positive or a negative number? It's positive, so it should be going, which is what is happening, right? So you guys, you got that all has to connect, okay? That all has to connect. If you knew it was increasing, you know your answer is going to be a what? Positive. So if it's negative, you did something wrong, and vice versa, right? So figure it out. So basically, what does this represent? Tell me what this means in the real world. The ladder's going up. How much? Feet per second, right? This is feet per second. Does everybody see how this is going? Are we good? Any questions on that one? You sure? All right, good. We're kind of no. What do you mean? I only have two platforms. No, you guys are on the exact same. I see y'all both. I see y'all both today. Are you smarter? I'm smarter. Alright, so we're on example 4. So if you missed example 3, too bad. A tank of water in the shape of a cone is leaking water at a constant rate of 2 cubic feet per hour. The base radius of the tank is 5 feet, and the height of the tank is 14 feet. So, situation, people, situation. Something's going on here. I have a tank, or you can even think smaller if you want to. I like to think of this as like a raspa cone, right? Everybody's eating a raspa. And it has water in it because I let the ice melt. Okay? And it's leaking at a constant rate of 2 cubic feet per hour. Okay? Now, for a cone, there's 2 measurements in a cone. There's a base radius and a height. Okay? Which part is the base? The top, the circle part, right? And if it makes sense, because it's called a base radius, right? Only circles have radiuses. Okay. So this has 2 parts to it. This has 2 parts. At what rate is the depth of the water in the tank changing when the depth of the water is 6 feet? And then part B is at what rate is the radius of the top of the water in the tank changing when the depth of the water is 6 feet? So first of all, guys, what's given? Tell me what's given. Okay, so I know the radius is what? 5 feet. I know the height is what? And actually something else was given. It tells me that it's leaking. It tells me that it's leaking. So guys, what does that represent? First of all, if you fill a tank with water, what are you talking about? If you fill anything, if you're filling it up with something, you're talking about what? Volume. We're talking about volume. Does everybody agree? We're talking about volume. So I know that the rate of the volume, basically I know dV/dt, right? dV/dt, the change in volume, is leaking at a constant rate of 2 feet. So my dV/dt is equal to what? You tell me. Is it positive 2 or negative 2? Why is it negative? Because it's leaking. It's decreasing. Does everybody see that? So this is a negative 2. We good? So that's all that they've given me so far. Okay? So this has 2 parts. Let's start with part A, obviously. It says, at what rate is the depth of the water in the tank changing when the depth of the water is 6 feet? So first of all, we already know we're dealing with volume of a cone. Right? What's the formula for volume of a cone? The formula. Good. Volume equals 1/3 pi r squared h. So this actually has 2 variables in it. This actually has 2 variables in it. So, surprise, surprise, if it has 2 variables, and what are they doing? So what am I going to have to use? Product rules. Everybody good with that? Okay, keep that in mind. So, this is the volume of a cone. As we've said before, What do I want? It says at what rate is the depth of the water? Good. So depth is another way of saying what? Height, right? Because it wants to know how tall it is, except depth usually means you're looking down on it, right? So that's the only difference. So does everybody agree that we want dH dt? Right? When what? When the height is equal to 6. So I want the dH dt when the height is equal to 6. Are we all good with that? Okay. So I know that this is my formula, so what am I going to have to do with this? Take the derivative. So help me out. Obviously the derivative of v is what? 1 dv dt. And so this is going to get tricky here. I know that this is a product rule, right? Which is the first part of my function? I would say I would do this. I would say there's the first part, there's the second part. Agreed? Technically, I mean, I guess I could move the 1/3 over here, give this pi and give 1/3, but why confuse yourself, right? So let's just keep that as f and this as g. So tell me what I have. 2/3 pi r dr dt times h plus 1/3 pi r squared times dH dt. Does everybody good understand what I just did? Right? We good? All right. So this is kind of some side work for me. Okay? So then this is the formula I'm going to use. Okay? Before I start plugging in, do I know, obviously I want dH dt. So this is the thing that I want. Do I know everything else? So do I know dV dt? Yes. Do I know an R? That's my initial R, but I want it when the height is what? 6. So that's kind of interesting, right? Do I know an H? H is 6 because it tells me when the height is 6. So does everybody see that I don't? And also, do I know the rate of which the thing is changing? No? So I'm going to have to do some more side work here. That's why this is our last example, because this one has a lot to deal with. So I do not know R, okay? And I do not know dr dt. Okay? I do not know R and I do not know dr dt. Okay? I could kind of figure out R by using, let's go back. What shapes do I have here? I actually have the triangles. Right? So cones are triangles. So I'm going to actually use similar triangles here. Okay? They are similar triangles. Does everybody agree that they are similar triangles? How do I know? Well, they have the same angles, right? They have the same angles, so they are similar triangles. So according to my similar triangles, the radius over the height is what? 5 over 15? 14, sorry. 5 over 14. So I'm going to just use ratios. With similar triangles, you can use ratios. Agreed? So my radius over my height is 5 over 14. Agreed? Solve for R. So R is equal to what? 5 over 14 times H. Is that acceptable now? Why? Because I know H. So I've related R to something that I do know. Does that make sense? Okay? So I don't really need to know R anymore. So that's one thing that helps me. So here's, what else do I need? What else do I need? I need dr/dt. Okay. So, isn't that what? Yeah. So, good question. Can I do that? Well, what is B's asking for what? So it's the same thing, right? So Vanessa, notice, look, in B they want us to find dr/dt, right? With when the height's the same. So why don't I do that one first? And that's gonna happen. I guarantee you that's gonna happen sometimes, right? Guarantee you. So again, in this case, we want dr/dt when the height is 6, okay? Which essentially you have to understand that this is the same moment as the first one. It's the same moment because remember, these are only moments, right? That height is only going to be 6 for a little bit because it's leaking, right? But it's the same moment, okay? So if the radius, we already know that r is 5 over 14h because we figured that out in the first part, right? So I can use this formula. So take the derivative. What is it? dr/dt equals 514 dh dt. Do I know dh dt? No, that's what, so then we couldn't do this one first. All right, let's go back. Let's go back. Okay. So we found r. We found r. We need dr/dt, right? So let's plug in. So let's plug in what I know. Let's plug in, what do I do know? What do I know? I know dv dt. How did I get my r to be 6? No. So if I use v equals 1/3 pi r squared h. Okay. So this is what I'm gonna do. This is what I'm gonna do. I figured out. So I did this for a reason. I did this for a reason. Okay. Because look, if I replace this, so v equals 1/3 pi 5 over 14 h squared h. Guess what? There's no more r. There's no more r. So I don't need to know dr/dt because there's no more r. Does that make sense? Okay. So can I simplify this here a little bit? Let's simplify this. So this becomes 1/3 pi 25 over 196 h squared times h, right? Everything's being multiplied. So this becomes 25 over 588 pi h cubed. This formula is a lot better because what don't I have? R or dr/dt, so then guess what? Got rid of it. I don't need it, right? I don't need it. So how did I do that? How did I get rid of my r? With my similar triangles. I use my ratios, right? I can use similar triangles. Basically, I eliminated. Could it have worked the other way? Right? It could have worked the other way. I could have gotten rid of the h by substituting everything with r. So now, at this point, take the derivative. So it'd be what? Well, dv dt equals 75 over 588 pi h squared dh dt, right? And then, of course, do I know so I still want the same thing, which was what? dh dt. Do I know dv dt? Do I know an h? So let's plug in and solve. So here's what I have. I'll have negative 2 equals 75 over 588 pi 6 squared dh dt. And does everybody see that these are all just numbers, correct? These are all just numbers. So dh dt is equal to, essentially, you can do this in the calculator, negative 2 over all that, right? So I would literally just type that in the calculator. Just type all that in the calculator. So negative 2 divided by 75 over 588 times pi times 36. And you get approximately you are missing something. You just guessing or what? Oh, yeah. Tell me what y'all get. Don't trust your classmates. Do it yourself. Negative 0.13. And then how many decimal places did I tell you how to use? 3. 3. So 3 decimal places. So it's 0.1386. So I'm going to say negative 0.139. Does that even make sense? That it's negative? Yeah, why? Because it's decreasing. So this represents my what? dH dt. This is my dH dt. Okay? So I know it got kind of confusing, but do you see what the trick here was? So the thing was this. When I started the problem, I would have done this, right? I would have done this. But then doing this kind of made me realize my issue. My issue was what? That I didn't know R and I didn't know dr dt. Okay? So we wouldn't have known that we needed all that stuff until I took the derivative. Okay? So I'm glad we did this on purpose because it kind of shows us, hey, there's a lot of things that I'm missing here. So that's when I said, okay, maybe we can get rid of R. How? Using what? Similar triangles. So my radius over my height is 5 over 14, so then my radius is 5 over 14h. So then I can go back to my original equation and replace my R in terms of h, right? In terms of h. So then when I do that, I get a new equation that then I can derive and plug in what I know to find what I need. We good? So then on part B, we kind of already started. It says at what rate is the radius of the top of the tank changing when the depth of water is 6 feet? So we used our similar triangles. R equals 5 over 14h. dr dt equals 5 over 14 dh dt. Now, it's very important. Do I know dh dt? So why can I use that one? Because it's the same moment. Had they said when the height is 5, could I have used the dh dt? No, because that's a different moment. Does everybody understand that? So you have to make sure they're at the same moment. Most likely they will be, right? Because if they were different, then we're starting a whole new problem and we're probably going to have a whole new set of issues, right? A whole new set of issues. So in this case, to find the dr dt, all I really have to do is plug in my dh dt. So 5 over 14 times my negative, 1.39. So what does that give me? .496, and this represents dr dt. Does that make sense? Does it make sense that my radius is getting smaller? Think about a cone, right? If you're looking down on it, it's a thing. Like I said, think about a raspa cone. If it's leaking from the bottom, which has happened to all of us, right? So imagine the top is a circle, right? The top is a circle, but what's happening to that circle as it's going down? It's getting smaller. So obviously the radius would also be getting smaller. Does that make sense? So related rates, guys. So related rates are exactly what it sounds like. You're just finding rates of different things, but everything is respect to what? Time. Everything is respect to time because that's the only constant that keeps going, but everything else is changing. Okay? So, very important that you remember some formulas here. So, you're going to get your assignment, and guys, the important part is, do I even remember what formula is? So, I'm going to have to start remembering volume of a sphere, of course, your Pythagorean theorem, which hopefully no one forgot, but volume of a cone, any kind of shapes that you can think of, things are going to happen to them, okay? So, if you don't remember, what are you going to do? GTS it. All right, for now, GTS it. And then remember.